Hey y'all, today we're going to be exploring heating and cooling curves and looking at how to read them. So, this is what a heating curve looks like. So, what a heating curve shows you is the phases of matter that a substance is in as the temperature is increased over time. So, we start at a cooler temperature, which means we actually start at the solid phase. So, this diagonal line right here is actually representing our substance in the solid phase. Okay. So as time moves on, temperature increases. So as we move across to that line, we reach this plateau. Now, what this first plateau stands for is our melting and freezing point. So this is the temperature at which our substance is going to melt or freeze. So I'm just going to put MP for melting point and FP for freezing point. Another term that we can use for this plateau here is called the heat of fusion. So there's actually a specific amount of heat that is needed to go through this phase change. As you can see, it actually takes some time as we're adding heat to this to fully get through our melting point. So we're fully transitioning from a solid to a liquid here as time moves on. That requires a goodly amount of heat depending on what substance you're working with. And so there is this heat of fusion that is associated with it. Okay, so again, now we have this next plateau and we have fully moved through our melting point, and this is now our liquid phase. So this plateau represents our substance as it's in the liquid phase. And so we're continuing to add heat over time. Our temperature is increasing until we get to our next plateau. And now this plateau is the condensation or evaporation point. So your evaporation point or your condensation point, again, just using EP and CP for those. So that's just evaporation point, condensation point. So this is the part where we're fully transitioning from a liquid to a gas. And this one is called heat of vaporization. So there's a certain amount of heat that is associated with this phase change. We are still adding heat here, even though we're not seeing a temperature change. We're adding heat over time. And so there is an input of energy, and that's going to be called the heat of vaporization. And then our next plateau, of course, is gas. Or sorry, not plateau, our next diagonal line, our next slope here is gas. And so that is a heating curve. It's just showing you the temperature where our substance exists as a solid, the temperature that it starts to melt, and then the temperatures at which it's a liquid, and then the exact temperature at which it starts to evaporate, and then the temperatures where it's a gas. And of course, this will kind of keep going on until we reach that critical point on like our phase diagram that we've been seeing. So if we reversed this and we cooled temperature over time, we get this cooling curve. And so instead of starting at a liquid, or excuse me, instead of starting at a solid, we start at a gas. And so this first slope here is a gas. Again, we're going to cool this substance, which means we're taking away heat. So this is going to be that condensation point in this case, or evaporation point. We're going to start condensing into a liquid here. And then we're going to keep going into this line here, which is going to be our liquid. And then we stop there. But of course, if we kept going, we would have another plateau and then another slope. And again, we would have our melting freezing point. And then we would keep going down into a solid. Okay, so don't get too confused when you see the opposite of a heating curve. It's just a cooling curve. It's basically a heating curve flipped upside down so that instead of starting at a solid, we start at a gas.